is August 25th, and we're going to be working on Pascal's principle. And Pascal's principle tells us three things, basically. I'll give you a second to get set up. It explains three behaviors of liquids to us. Three behaviors of liquids. So, just down where you can see. The first one is it tells us that, or it explains how pressure increases with depth in the fluid. So we're going to start with that one, and you might want to leave space for the other two because we'll get to them. But I'm going to do the first one, and then we'll do the second one, and then do the third one. And we'll hope the guy mowing the yard doesn't run into the wall like he always does. It's always upsetting. Y'all have been in here when that happens, yes or no?
Yes.
Some of you have. Minding your own business. Wham! Oh, ran into the wall again. Okay. So, pressure increases with depth. So you guys probably know, and we talked about it, I think, a little bit last time, that if you go scuba diving or you go diving with a tank, that when you go diving in the ocean, the lower you go, the more pressure you experience. And if you go low enough, it can kill you, right? We talked about how if you go low enough, it causes all the gases in your body, like oxygen and nitrogen and things like that, to actually turn back into liquids because you squish the gas so much that instead of it being a gas now, it's turned into a liquid because you push the particles so close together. Okay. So, when we do this, why does that happen? What's the underlying piece? Sorry, the pollen's killing me right now. So, let's imagine right here we have our tank of water, and I'm looking at one little particle in here. And what forces does this little particle have? Well, the particles below it are pushing it up. The particles at every side are hitting, because in a liquid the particles are free to move, so they're banging around on each other, but they're still staying pretty close to one another. So the little particle right there would have lots of forces acting on it, front to back, up and down, left to right. And from Physics 1, what do we know that Newton's second law said about net force? Let's see if we can remember that. If we have a net force, what has to happen? That's the third one. So every particle that pushes on ours, our particle will push back on that one with the equal force in the opposite direction. But what happens if we have a net force? An extra. What? We're going to change the velocity. So if there's a net force, the particle is going to move. It's going to accelerate, right? So if any one of these forces in this picture was bigger than any of the other ones, if the forces are unbalanced, and let's just for argument's sake, let's say this one is unbalanced. It's bigger than its counterpart on the bottom. If the forces are unbalanced, if this one's larger than this one, the particle will have to accelerate up. But Pascal's principle is working on stationary fluids. So what do we mean by that? Well, does that mean the particles don't move? No. They're kind of moving up and down and in and out a little bit. But I don't see a mass movement of particles towards the top of the water. I don't see a mass movement of the particles to the left or to the right or down. That little particle that's in the middle of my water is basically going to be jostled around right there in the middle of the water. You okay with that? Unless there's a net force. But if there's a net force, the particle has to move. Well, if the net force is up, where's that particle going to go? Up. But now there's a gap where he used to be. So what's going to happen there? It's going to get, somebody below him may move up, or somebody on the side might fall in, or somebody above him might fall down, right? So if the forces are unbalanced, then these particles would constantly be moving up and down and left and right and all over. When we talk about stationary fluids, we kind of assume it's like you guys in your seating chart. You're free to kind of wiggle around, but you stay there. You don't wiggle so hard that you come out of the chair. Okay? So Pascal's principle is going to apply to stationary fluids, not moving fluids. At least not yet. We'll have to talk about that as we get there. So what does that mean about this particle? Well, this particle, Pascal says, all the forces are balanced on the particle. Which means that if you think of this as a, let's look at it from a more particle stance. Here's my water. If I think of this as a thin sheet of water, let's imagine we had a water tank. We have a thin sheet of water. And I'm going to move it over where you can see. Yeah, I got you. So I have a thin sheet. So I'm at some height or depth in the fluid. All these particles that are on that sheet are not moving up and they're not moving down. They're basically stationary, which means our forces have to be balanced. What forces? What forces act on that sheet, that thin layer of water? Don't think particles, think sheet. Like it's one big solid like Jell-O. Like instead of water, you have Jell-O and you just take a thin slice out of the Jell-O. Gravity is going to act on it. From what? Its own weight, right? It has a weight, so there'll be a gravitational force on the sheet, on the piece of Jell-O. But what else acts on that? What do we call it a normal force? If we're using the continuity model, you can think of it as a normal force. So the water that sits above our slice would be in contact with our slice. So all that water pushes down. Your particles don't come into me, my particles don't go into you. So it's kind of like a normal force. But there's also air sitting on top of the chunk we've got between us and the layer. So what we've got to deal with is if I have a sheet at this height, there's going to be a force down from the liquid above and a force down from the atmosphere. So the atmosphere pushes on the top layer of water, and then the top layer of water pushes on my sheet, then my sheet pushes on the water below it. So far, so good? So what you have to do, let me zoom down just a little bit and see all of that. So what we have to do is to find the total, since pressure is pressure total, will be pressure from the atmosphere plus pressure from the gauge pressure. This one comes from fluid we are in. We call it gauge pressure because it ignores the atmospheric. Like Luke, if you go fill up your tires with air, there's a number on the side, right? What's your number for your tires? I bet you know this. Do you know this or do you not?
34.
Okay, so 34. And it says pounds per square inch because we're British Imperial. So what Luke does is he goes and he puts air into his tires if one of them goes flat or if it's gotten cold and now the air is compressed, right? So you want to buy gas when? When do you want to buy gasoline? Hot or cold?
Cold.
Cold, because it's more dense. And you want to sell things when they're high because they fill a bigger volume, right? But you guys know that on that first cold day, when we really have a nice cold first day, a lot of your tires will look a little flat on the bottom till you drive them. It's because the air is compressed. Or the nitrogen is in my case, because I have nitrogen in my tires. They're less corrosive. But anyway, 34. That number is a gauge pressure because it's only the amount of pressure inside the tire. It does not consider atmospheric pressure. It's just how much pressure do I need to have inside my tire. The reason for that is if you had to add atmospheric, it would be several thousand pounds per square inch. And looking with a gauge that had like 14,602 to 14,636, that's not a fun gauge to use. So what we do is we just consider the inside part. So we call it a gauge pressure. Some of you know the helium balloons that they blow up, it's got a pressure gauge at the top. That pressure gauge is only for what's inside. Or let's say that Josh decided to go play soccer this afternoon. Probably not with your knee, but you could. If he goes and plays soccer this afternoon, he might want to make sure that the soccer ball is inflated. I think those are 9 to 11 pounds or 9 to 13 pounds of pressure. That is just the number that goes with inside the ball. So gauge pressure is just how much you've got inside. Total pressure is whatever you got inside plus the atmosphere. You always have to consider the atmosphere here on Earth. If you were to go to Mars, guess what you would have? Only gauge pressure, because the atmosphere on Mars is non-existent. Which is why if we send people there, we have to send them with structures that can protect them from both the UV radiation and the no atmosphere thing. Which is why it gets really, really hot and really, really cold. We have a blanket. Our blanket's about 6, 7 miles up. And actually the atmosphere goes a lot further than that, but the thickest part, if you like the fleece part of your blanket, is Mount Everest and down. A little above that. Okay, so what if I was to do something fun like this? Remember we called this is called a manometer. There'll be a tube over here with our pressure gauge attached to it. Let's say that over here I have a layer of canola oil, and then I have a layer of water, and then for some reason I decided to put molasses in here. What would the pressure at the bottom of the tank be? Well, it would be pressure due to the atmosphere plus pressure due to the oil plus pressure due to the water plus pressure due to the molasses, because this is at the bottom. So a point down here is feeling atmospheric, is feeling these layers of oil, and a point here would have to be balanced. So the push from the left would have to be equal to the push from the right. And so the liquid would go up or down based on how much atmospheric pressure there is. Okay? So in this case, the way we would work this problem, if I just want to know the pressure at this point, I'd add up all the things that are above it, whether they're directly above or not, because we don't care. We only care if a point is below a column anywhere, it's below every column. I'm going to draw a picture of that here in just a minute. And then if we open it to the air, then we can figure out what atmospheric pressure is that day, because it would have the same weight of air as we have weight of junk, fluids, on the other side, because we're balanced. Am My fluids would not be doing this in the U-tube. Got air here and air there. And I'll stop and take questions. So far, so good? So what they're doing when you take your blood pressure is it uses a device sort of like that, and they close the side so that the tube is now completely sealed. And they do what to you? They squeeze your arm, right? Which means you put pressure on it, which leads us to our second point, is that a pressure applied anywhere becomes a pressure applied everywhere. So when they squeeze your arm, it constricts the blood vessels. If it constricts the blood vessels, it makes the pressure in your blood vessels go up, because you've put a new force in there that wasn't there before. More force, same area, or more force in this case, and constrict it, less area. Then you can see the pressure in there. We'll talk about why they do that. So here's point number 2. Yeah.
See how hard your heart pumps?
Yes. Yes, it is. And there's a little more to it. We'll talk about it, but because that's what we're fixing to talk about. This would be extra forces are transmitted everywhere. So, a new force or extra force is applied anywhere becomes an extra force everywhere. I do not see a beaker. There's my scale. I'm going to see if I have a small glass jar that I can use, or a cup. Okay. We might do it next time. If you take a beaker full of water and you put it on a balance scale, it's going to tell you the mass of the scale, right? You set it on, they'll say whatever grams or kilograms. What happens if I push my finger down on the water? Does the scale reading change or not change? I'm not going to push my finger into the water. I'm just going to push down on the water. Will the scale reading change? I don't know. Got to vote for... I don't know. I don't know seems to be a choice.
I'm guessing so.
Yeah. So I'm looking for a cup. We'll go see if I bet I know where I can get one. So we put water in the little bucket. We saw the mass of it, right? And the mass of it was 450, looks like 450.9. What happened when you pushed on it? It goes up, doesn't it? And then, of course, if some sticks to your finger, overall it goes down. That's weird, yeah? Because you're not actually putting your body in the water. The water is not supporting the weight of your finger, right? And yet somehow it feels that new force. But they feel new force because you did what? You pushed on the water. So, when we push on the water, even if we're not supporting the weight, even if we're not like a raft or a canoe floating in there, it reads the weight of the water. So, this is the second piece. Pressure applied, extra force. Ooh, I'm shiny. Force applied, extra forces are transmitted everywhere. So the bottom of the water felt the push on from the top. And that's kind of weird. Okay? So, that's the first one. So, what happens if or second one. So, when we're talking about the blood pressure, when you measure your blood pressure, you do it in two situations. Here's your nice, cute little capillary. And what happens when your heart pumps? When it beats and squeezes together, what happens to the blood in that blood vessel? It's going to run through, Does the blood vessel stretch a little or not? If you don't know anything about medicine, huh? It probably does a little bit, yeah? Especially around your heart, because you're squeezing it out of your heart to go into the arteries. And then it opens up, and you've created a lower pressure area, so the blood gets pushed in on this side of the tube, comes in on the other side. So they measure two different things. They measure the push, as you said, so that if I squeeze more liquid in here, I get a tiny little bit of push out everywhere. So when they measure your blood pressure, they put the cuff on your upper arm, close to where your heart is, because it's at the same depth of fluid. So now we're getting the same pressure in my arm as I should see at my heart. And they measure it 2 times. They squeeze you tight, right? And they measure the push, and then they squeeze it with the low pressure when it has relaxed. And if you have too much outside of those pieces, if you get a really high number for the top one, what does that tell me? It's high blood pressure, right? Like it's supposed to be somewhere below 120 over 80, 121 over 80, somewhere in that neighborhood. If it gets above that, what it means is when your heart's beating, it's too much pressure on your blood vessels, too much pressure on your heart, which means too much force on your heart, right? And that means your heart is having to work really hard to pump blood. Those are the people that a lot of times will pass out when they're working out or exerting themselves. Okay? And then the other side of it is if it drops too low, that means that it's not flowing through easily the other way, so that when it expands, the blood is not flowing into your heart like it should. So you're kind of getting this janky push and pull. All right? That is the very non-medical way to talk about this. It's a very physics way to think about that. But that's why they measure it, is because they want to know what your heart's doing. And so when we study exercise, we need your blood pressure to be good, but we also want your heart rate to be good. Because a high heart rate indicates it's having to push more times to get the same effect. So there's some other pieces, not just how hard is it pushing. Okay? All right. And that's kind of the idea behind the second piece. And then the third piece is hydraulics. This explains hydraulics. Hydraulics. So hydraulics work based on Pascal's principle. So I'm going to put this over here in the corner and talk about that a little bit. So, you guys know that you have, in your car, you have a brake pedal that somehow is connected with a little tiny tube of some sort to something that's got brake fluid. I may not know much, but I know there's brake fluid in there. I don't know what it is. I don't know why, but somewhere over here on this tube, it does its thing, and it comes out over here onto and this is not drawn in the shape at all, but it's pushes into a brake pad. This is very bad car work, okay? So just remember, we're trying to teach physics, not how your car actually works or how you would have to repair it. Just keep that in mind. But if I push, we all know too that if I was driving down the street, it's not like when you were a kid on a bike. If I'm driving down the street on a bike, riding on my bike, I could put my feet down and skid to a stop. Right? Have we talked about this before in here or not? I don't think we did. Okay. So I would put my feet down, like if you were lazy or you had a bike like I did that was a hand-me-down from a cousin, it didn't have bike brakes. So the way you stopped was literally to put your feet down and allow friction, and then your mom yells at you because you're wearing out your tennis shoes, and you're like, but you bought me a brake that my bike doesn't have any brakes on it, so you got to pick. So anyway, you can do that when you're doing that with a bike. It's not always the best plan, but you can stop. If I was to do that with my car, I'm driving along, I need to park. Open the door, stick a foot out. How's that going to go for me?
Poorly.
It's going to be bad, right?
We'll stop eventually.
Yeah. And by eventually, that you really do mean eventually. And probably the way you stop is not going to be pleasant, because the friction would go pretty high and your shoe would melt. You probably know that this time of year, a lot of the major league ballparks that use AstroTurf, the players have to be really careful because their cleats will actually melt on the field. It's so hot. Which is one of the things that worries me about our new beautiful football. I love our new beautiful football field, don't get me wrong. But they put in not turf. They put in a different material because turf gets really stinking hot. And we live in Tennessee. So, but back to the main point. When you do that with a car, you can't do it because your car is so heavy, right? So massive that it's hard to stop. It has a lot of momentum. All right, so what are we going to do here? Well, I push on the brake pad, or the brake pedal that's in my car, which then transfers the force miraculously through brake fluid to a brake pad that smooshes on the side of the tire. And actually, all four of them smoosh on the side of the tires, or front wheel drive and back wheel drive and whatever janky thing you built in your own garage, kit cars, and it stops the car. How does that work? Because do you really have to mash down on the brake pedal to make your car stop? Like, is this a stop kind of thing? Or is it more like tap, 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 tap? It's closer to the tapping, right? Or maybe kind of a steady push down. But you don't feel like you're lifting weights to do this. Is that fair? So how can I apply that little tiny force and somehow miraculously I get the whole big car to stop? Or even better, how do I apply that force in a bus and get the bus to stop? Or a semi? Well, it goes back to what's true about fluids. Are they compressible or not compressible? Not very compressible. And so when I push down here on this side, every little particle inside that tube feels the new force that I applied. But here's the bonus feature. The formula for pressure is force over area. And you know what? It's always force over area. Force 1, area 1. Force 2, area 2. Let's make up some easy numbers. Let's say you apply 100 newtons of force, and the area of the little tube by your foot is 0.1 meters squared. We'd find the area of that circle. Okay? Let's just make it 1/10 of a meter. All right. What does that mean on the other side? Well, let's do this. What if the area on this side is now 0.5 meters squared? What does my top number need to be? It needs to be 500 newtons. Looky there. I just pushed 5 times as hard simply by changing the area that I push on. And that's the whole principle behind hydraulics. Some of you have a foot jack for your car. You pump down on the foot pedal, and it pumps your car up. Usually it has compressed air or something in it. So you apply your force on a little tiny hole, and it takes it out to a really big hole, and that whatever the difference in the areas is becomes the difference in the forces. So you multiply your force. Now here's the downside. The downside is you have to trade force for distance. So if I'm pushing on a little tiny one, I have to push farther in this way. For example, I push farther in on the brake pedal, then the brake pads move out. So the first movement is a big one, and the second one is a small one. So for example, I might have to push the brake pedal until it's over here, and this guy would only move just this little tiny distance out, so that we have a new hole on our new sheet. It's only moved this far, where this one has had to move a bigger distance. So we trade a force for a distance. Which means, what are we going to have to do in this case? Well, if we multiplied our force by 5, the brake pedal would move 5 times as far as the brake pad moves. So if the brake pedal moved 10 centimeters, the brake pad would move 2 centimeters. You have to give something to get something. But the cool part is we could take a mouse. If we put a mouse on a little tiny platform and we put an elephant on a really big platform, the mouse by itself could bounce the elephant. Could climb up there and the elephant would go up because of the multipliers. But the mouse would have to go way down this way and the elephant would only go up a little tiny bit. But we could make the elephant be lifted up by the little tiny mouse. And that's the whole principle behind hydraulics. Okay? So far so good? Okay. So I'm going to stop right there and then I'm going to let you get back to the lab and